Picture a routine database operation, transferring $500 from account A to account B. The database engine issues an update statement, deducting $500 from the first account. But in the exact microsecond before the second update credits account B, the server loses power. The system goes dark. Account A is officially down $500, but account B has never received it. So where does that money actually go? In a naive data storage system, that money is permanently destroyed. The data is corrupted because an operation was sliced in half by a hardware crash. Relational databases prevent this by grouping multiple commands into a single, indivisible operation. Systems engineering must account for the certainty that hardware and networks will fail mid-process. Data is only useful if its accuracy can be guaranteed through those failures. The mechanism that provides this guarantee is the transaction. A transaction is a logical unit of work, a sequence of operations that the database treats as a single, indivisible action. Both steps of the transfer must happen, or neither. This indivisibility is governed by 4 strict rules, known universally as the acid contract. First, atomicity. Partial success equals total failure. Second, consistency. The sum of accounts A and B must remain equal. Third, isolation. Mid-transaction states are hidden from concurrent queries, preventing dirty reads. Finally, durability. Committed changes survive catastrophic system crashes. The ACID contract provides the predictability and fault tolerance required to run modern applications in highly concurrent environments. High-level theory is useful, but the actual mechanical plumbing inside the database engine is what executes these rules. A transaction does not instantly succeed or fail. It traverses a strict internal lifecycle. This is the formal flowchart that maps the transaction state diagram. Every transaction navigates these exact nodes. It begins in the active state. This is the initial phase, where the transaction executes its reading and writing operations in memory. If normal execution can no longer proceed, due to a logic error or hardware loss, the path diverts to the failed state. From failed, the database actively rolls back all changes, pushing the transaction to the aborted state. This restores the pre-transaction data, preserving atomicity. But if the operations finish without error, we enter the partially committed state. This is a precarious middle ground. The logic is complete, but the data is not yet safe. Only when the data is written to persistent storage do we reach the committed state, the terminal phase of success, where durability is finally achieved. Navigating these explicit states correctly is the only way a database engine can actually uphold the ACID properties in practice. Let's map our $500 bank transfer precisely onto this state machine. On the top left, we have the executing SQL script. On the top right, the state machine. And on the bottom, the physical hardware separating the volatile memory buffer from the persistent disk. As the transaction initializes, we enter the active state. The engine reads account A and calculates the deduction. The new balance is updated in the volatile memory buffer. During this active state, the physical disk has not been modified. The altered balance exists entirely in RAM. Next, the engine reads account B and adds $500, again updating only the memory buffer. The script executes its final logical statement. This transitions our state machine from active to partially committed. The application-level code has finished running, but the database engine considers this data highly vulnerable because it hasn't touched persistent storage. The partially committed state is the most dangerous phase of the lifecycle. The SQL is valid, but the system could still crash and lose everything. To bridge volatile memory and persistent disk safely, the database relies on the write-ahead log, or WAL. The database issues an operating system fsync command, instructing the hardware to flush the transaction record directly to the write-ahead log on the disk. But what happens if a catastrophic, unexpected hardware crash hits the system just milliseconds before that flush completes? Because the hardware crashed before the disk confirmed the write, the transaction state collapses to failed. Upon reboot, the database's recovery manager sees the incomplete record. It forces the failed transaction to abort it, instantly erasing the memory buffer changes and preserving atomicity. The money never left account A. Contrast this with the success path. The fsync command completes flawlessly, and the transaction record is secured on the persistent disk. The state machine crosses the threshold into the final committed state. Durability, the absolute guarantee of data survival, is achieved exclusively at this exact boundary. Everything prior is just an illusion of safety. Understanding this mechanism is where theory meets production. Confusing these states is the fastest way engineers fail system design interviews and corrupt databases. The first major pitfall is assuming that executed code equals durable data. Look closely at the edge between partially committed and committed. Flawless execution in the application layer means nothing if the system crashes before the state machine reaches that final committed node. The second pitfall is relying on implicit auto-commit. Here are two independent update statements without a transaction block. By default, the database treats each as an isolated transaction. If the first commits but the second fails, your system is left permanently out of sync. Assuming the database handles complex logic automatically without explicit architectural boundaries is a guaranteed recipe for corrupted production systems. A transaction is an indivisible, ACID compliant unit of work that is only truly complete once the state machine transitions from memory to persistent storage. Internalizing that boundary separates a basic developer writing queries from a systems engineer building robust infrastructure. Keep analyzing the systems you build, and we'll see you in the next breakdown.